Okay, so today we're going to learn a little bit more about parallel and perpendicular lines, and we're going to get into parallel and perpendicular lines, theorems, and postulates, which help us understand relationships. So, parallel and perpendicular lines. So parallel lines are those lines that are coplanar. So lines on the same plane that do not intersect. So parallel lines are lines that are coplanar on the same plane but do not intersect. Perpendicular lines, on the other hand, are again coplanar, so they're on the same plane, but they intersect at a 90-degree angle. Perpendicular lines have to intersect at a 90-degree angle. If they do not intersect at a 90-degree angle, they are just intersecting lines. They are not perpendicular. So in order for lines to be perpendicular, they have to intersect at a 90-degree angle. Just a reminder that coplanar means that they lie on the same plane, and a plane is basically a two-dimensional object that extends infinitely in both of its directions and has no height. So both parallel and perpendicular lines have to be on the same plane. Those lines have to be on the same plane, but parallel lines do not intersect and perpendicular lines do intersect. So we're going to look at our first theorem for today. This one, the shortest distance theorem. This basically states that the shortest distance from a given line to a point not on that line is the length of the segment perpendicular to the line through that point. So basically, if I wanted to find the shortest distance between this line AB and this point C, the shortest distance would be a segment which runs perpendicular to my line AB. So if I created a line right there, and that line was perpendicular to my line AB, then that would be the shortest distance to that external or that other point C. So this line would be the shortest distance to that point C. Okay, so that's the shortest distance theorem. We also have the parallel postulate theorem, or the parallel postulate, which basically says, given a line and a point not on a line, there exists exactly one line in the same plane that passes through that given point and is parallel to that given line. So basically, if I have a line and I have a point, through that one point, there exists one and only one line which runs through that point and is parallel, so it never intersects with my original given line. So these two lines would be parallel, and that black line represents that one and only one line that would run through that point, making those two lines parallel. So that's the parallel postulate. Now we're going to learn about something new, skew lines. So skew lines are lines that are not coplanar, so they are not on the same plane, and they do not intersect. So it's a little bit like parallel lines, but skew lines, on the other hand, are not coplanar, so they're not on the same plane, where parallel lines are on the same plane. So skew lines not on the same plane, but still do not intersect. In the diagram, we have plane R and we have plane W. Plane R and W are parallel, and they contain two lines. In plane R, we have line DE, and in plane W, we have line FG. Because these two lines are on two planes, they are not on the same plane, they are non-coplanar. And because they do not intersect, they are skew lines. So DE and F2 would be skew lines. Perpendicular lines are not skew lines because they exist on the same plane. In order for two lines to be skewed, they cannot be on the same plane. And perpendicular lines are not skew lines because they are also on the same plane, and perpendicular lines do intersect, whereas skew lines are not on the same plane and they do not intersect. So that is skew lines. So why is this important? Well, you might encounter something that looks like this, a question that looks like this. And in this question, you might be asked to identify any parallel, perpendicular, or skew lines from the diagram. Well, we just discussed the criteria for parallel, perpendicular, and skew lines, but I'll go ahead and go over it. Parallel lines are coplanar, and they do not intersect. So they are on the same plane, and they do not intersect. Perpendicular lines, on the other hand, are still coplanar, so they are on the same plane, but they do intersect, and they do so at a 90-degree angle. Skew lines, on the other hand, are non-coplanar, so two lines not on the same plane, and they do not intersect. So that's the different criteria for all these different lines. Based on this criteria, we can identify parallel, perpendicular, and skew lines in this diagram. So the first one, parallel lines? Well, the parallel lines that I can identify in this diagram are P and M. These lines are parallel because they are on the same plane, plane A, and because they never intersect. And we know this because of this symbol right here, which tells us that those lines can extend infinitely in both directions, but they'll never intersect each other. And so because of that, we can say that line P is parallel to line M. This symbol represents parallel because it basically mimics two parallel lines. So line P is parallel to line M. What about perpendicular lines? Well, in order for two lines to be perpendicular, they need to be on the same plane, but they need to intersect at a 90-degree angle. Well, what I notice is I have two lines right here that intersect at a 90-degree angle. That's what that box indicates. And those two lines do exist on the same plane, plane B. And so because of that, I can say that line L and line M are perpendicular to each other. So L is perpendicular to line M. And I use this symbol to represent perpendicular because it basically mimics how those two lines interact with each other or intersect each other. Okay. And then lastly, I have skew lines. Remember that skew lines are non-coplanar and they do not intersect. So because they are non-coplanar and I only have two planes, I need one line from plane B and one line from plane A. And I need those two lines to never intersect. Well, that being said, I can say that line M and L are skew lines because they are two lines on different planes, not coplanar, and they do not intersect. So L and M. But I do also have another pair of skew lines. Again, I need one line to be on A and one to be on B. And the lines that are skew are P and N. Those two lines are non-coplanar, they're not on the same plane, and they do not intersect. So P and N. So by doing this, identifying the different criteria for parallel, perpendicular, and skew, I'm able to identify these types of lines on this diagram, which is the type of problems you might encounter when it comes to identifying these things. Okay. All right, we're getting close to the end. Next thing we're going to look at is the perpendicular bisector theorem. The perpendicular bisector theorem basically says the points on the perpendicular bisector, which is a line ray or a line segment that intersects a segment, is perpendicular to the segment at its midpoint, are equidistant from the endpoints. So, what is a perpendicular bisector? Well, a perpendicular bisector basically meets this line segment QR, so it takes QR and it bisects it perpendicularly. So it's a perpendicular bisector. And that means because it's perpendicular, that means it meets it at a 90-degree angle. And the term bisector means that it cuts it into two congruent halves. So say that QR, line segment QR originally was 12 units. Well, the perpendicular bisector would cut it into two congruent halves, so 6 and 6. Okay? So that's the perpendicular bisector. But basically what this theorem is stating is that any point on this perpendicular bisector is equidistant from either of the endpoints. So it's equidistant from Q as it is from R. So because of that, we know that these two line segments would be congruent to each other. So they say this is point L. L is 8 units from Q. Well, then we would know that L is also 8 units from R. So that point is equidistant from both of those endpoints. Okay, so that's what we know about the perpendicular bisector theorem. So say that we wanted to answer a question using the perpendicular bisector theorem. Well, here we have, what is the length of segment AC? Line L is the perpendicular bisector of AB. And point C is equidistant from the endpoints of the line segment A and B. So basically, point C is equidistant from A as it is from B. Well, if it's equidistant, then that means that the length of AC and BC are the same. The length of AC and BC are the same. So let's plug in those equations. It is equal to, and what we're going to be able to do with this is identify X, and then we're going to be able to plug X back in. So plus 5 for X equals 3X plus 7 minus 3X. So what we're doing is we're isolating X. X is equal to 7. Once we identify X is equal to 7, we can solve for the length of line segment AC by just plugging in that X. So 4, 7 minus 5, 28 minus 5 equals 23. So AC is 23. Well, what does this tell me? Well, this also tells me that this is going to be 23 units because C is equidistant for A as it is from B. And if I wanted to check that, I could plug that in too. And that does in fact give me 23. Okay, so that's what we learned about the perpendicular bisector theorem. Not only does that perpendicular bisector create two congruent halves right there, it also contains points which tell me that the distance between that point and those other endpoints, endpoint AB, are also equal to each other. Okay. And then lastly, that takes me into the converse of the perpendicular bisector. Remember that the converse basically just changes the hypothesis to conclusion. So basically, it will just change the theorem that we just looked at around. So the converse of the perpendicular bisector basically just says, if a point is equidistant from the endpoint, then it is on the perpendicular bisector of the segment. So before we were told if we have a perpendicular bisector, then any point on it is equidistant from the endpoints. The converse of this switches that around, and so it becomes if we have a point which is equidistant from the endpoint, well, then that point must be located on the perpendicular bisector. So basically, it just takes the hypothesis conclusion and switches it. So basically, if I know that point P is equidistant from A as it is from B, well, then I can just assume that that point must lie on a perpendicular bisector, which would intersect my line segment AC into two congruent halves. So basically, it's doing the opposite of what we saw before, but it's telling us the same relationships between all these different line segments. Okay, any questions about this? So just to review, we looked at parallel lines, perpendicular lines, and skew lines. Parallel lines on the same plane never intersect. Perpendicular lines on the same plane intersect at right angles. Skew lines, different plane, never intersect. That was the relationships that we looked at before in between those. Next thing we looked at was all these different theorems and postulates. The shortest distance theorem, which had to do with perpendicular lines. The parallel postulate, which obviously had to do with parallel lines. The perpendicular bisector theorem, which had to do with perpendicular lines. And the converse of the perpendicular bisector theorem, which again deals with perpendicular lines. Therefore, we looked at different relationships between parallel and perpendicular lines. Any questions? Okay. If there's no other questions, I will not see you tomorrow. Just make sure to do your check-in, submit your independent practice. But I will see you on Friday. Bye, guys.